Good morning, everyone. Today's first talk is by Tsachik Gelander, and his affiliation says Weizmann Institute, but he's in Northwestern University. Okay, so the title of the talk is Spectral Gap for Irreducible Subgroups and a Strong Version of Margulis' Normal Subgroup Theorem. Tsachik, you may go ahead sharing your file.
Okay, so yeah, I apologize for not being there physically, but yeah, okay. So I speak about a new work in progress. The title is Strong Normal Subgroup Theorem and Strong Approximation and sorry, Spectral Gap for irreducible higher rank lattices, and this is a joint with Uri Bader and Ariel Levitt. So let me recall, so the talk is 50 minutes, right? Okay, so let me recall, sorry, it's 1 hour or 50?
Till 10 o'clock.
Okay, so let me recall the normal subgroup theorem of Margulis. Normal subgroup theorem. It says that in higher rank, lattices are as simple as they could be. So of course they're not simple because they're linear groups, so they're residually finite, but it says that every normal subgroup, which is not central, is a finite index, so every proper quotient is finite. So let G be a semisimple Lie group, center-free semi-simple Lie group of rank at least 2, and let gamma be an irreducible lattice, then if then any normal subgroup in gamma, which is not trivial, is a finite index. So the example, you can take G to be SL3R and gamma to be SL3Z, or G to be SL2R cross SL2R, and gamma to be SL2 say Z square root of 2. This is an irreducible lattice. And so this is a remarkable theorem. In several occasions, I think Margulis said that this is his favorite result or his favorite proof, and the proof is indeed quite remarkable in several levels, both in the basic idea and both in the details. The basic idea is that Margulis proved that gamma mod n is finite by showing that it's both amenable and admits property T. So Margulis proved that gamma mod n is finite by proving T plus amenability. So amenability and T and property T are two analytic properties of groups that don't get along together. And the tension between these two properties implies finiteness. Yeah, so let me recall the definition of amenability and property T, because we will use it. But before that, let me just remark that the first example I gave, SL3R, has property T, and therefore also gamma SL3Z has property T. So that part we get for free in this case. And by Kazhdan, the classical theorem, and also in other cases, so it is known that for most high rank groups, they have property T. And therefore all lattices have property T, and every quotient of a lattice has property T. So this part comes for free, and for that particular, in that particular case, Margulis only have to show that gamma mod n is amenable, which makes the proof simpler. The other example, when G is SL2 times SL2, it doesn't have property T, and in this case, he had to work harder to prove that gamma mod n has property T. And indeed, he published it in a separate paper. It's a technical and hard paper. And another proof of the difficulty of this case is that I think, so Margulis says this wonderful book about, which is, if you want, the Bible in this theory, and it has so many, and everything there is doing with absolute details, except I think the only theorem that it doesn't prove completely is the normal subgroup theorem, when G doesn't have T. So in the higher rank case without T, he only proved it in the book for co-compact lattices. But in the paper, of course, he do it in general. So and indeed, since Margulis proved this normal subgroup theorem, there has been a lot of improvements, a lot of papers that improve the theorem, but there was no improvement in the case where G doesn't have T. There was no, I mean, it was extended, but to other groups. But in the classical case of SL2R times SL2R, I will demonstrate some other improvement of Margulis normal subgroup theorem which are still open in that case. So let me first recall what is amenability and property T. Because it is crucial here, and for that I need to recall what is the notion of asymptotically invariant vectors. So let pi be a unitary representation. So you have a Hilbert space and the unitary group, and you have be a unitary representation. So pi has, we say that pi has almost invariant vectors or asymptotically invariant vector if there is a sequence Vn in H of unit vectors such that, so here I distinguish between the case that G is discrete and the case that G is non-discrete, locally compact. So in the discrete case, such that pi G Vn minus Vn, so this becomes is asymptotically invariant. So for any G in G, that's if G is discrete. And if G is not discrete, then you require almost the same, but the supermum of pi G Vn minus Vn where G belongs to K, this goes to 0 for any K compact. Then we say that the sequence Vn is asymptotically invariant and pi is asymptotically invariant vectors. So both property T and amenability are defined using this notion. So you can also define both property by fixed point theorems, so I don't know if you see, I wrote more stuff than I see on the screen, but so I'm not sure about the connection, but I'll assume that you see that.
We are not seeing anything about. Oh, now it's coming. Only
Okay.
pi TV.
Yeah, okay. This I wrote that a minute ago, but yeah. So I will wait a minute. So yeah. So then we say that pi is almost invariant vector. So I need this notion of amenability and property T for this talk, and then you define the following. So G has T if almost invariant vectors implies invariant vectors. What does it mean? It means that if you have a representation, a unitary representation which has almost invariant vector, then it has an invariant vector, a vector which is fixed by the group. So this is a property T. And Kazhdan defined this miraculous property, which became one of the most important analytical property of groups, with application to all fields of mathematics, basically. And he just defined it to show that lattices in higher rank are finitely generated and admit finite abelianization, but then it becomes extremely important. The definition of amenability is as follows. So G is amenable if L2 of
We
G.
lost you for some time. So after the definition of T property.
Yeah, after the definition of T, I praised this property and I said that it is one of the most analytic properties of groups, and it has many applications to all area of mathematics, basically. And then G is amenable if you look at the regular representation, G acting on L2 of G, or square integrable function on G. So G is a locally compact group or discrete group, so there is a Haar measure, and you can consider the space of all square integrable functions, and G acts on it by left multiplication, say. And G is amenable if this representation has almost invariant vector. And then it's an easy exercise that T plus amenability implies that G is compact or finite if discrete. Why? Because if it's amenable, then it has almost invariant vector, the L2 of G. But then by property T, L2 of G has invariant vector. Invariant vector is a constant function. Now the constant function is square integrable if and only if G is finite or compact. So T plus amenability, T and amenability are two analytic properties that don't get along together. The tension between them is what is the idea behind the normal subgroup theorem. And now, if G has T, so this is a remark. If G has T, if and only if lattices in G, well, this is a lattice, and this implies, and this implies that that every quotient of is T. So if a group is T, then any quotient of it is T. So in the case where G has property T, at least half of the theorem is given by Kazhdan, is already given. So we don't need to show property T, we just need to show amenability. And this is what allows many extension and generalization of the normal subgroup theorem for the case where G has property T. So yes, so I want to give another definition related to amenability. So let me say, not just for normal subgroup. So let's say that a subgroup delta inside a subgroup gamma, a subgroup delta of a discrete group gamma is coamenable, or let's say of G. Delta inside G is coamenable if L2 of G mod delta has almost invariant vector. So this is this is to be coamenable in G or to be coamenable in gamma. So a normal subgroup is coamenable if gamma mod n is a amenable group, but here I don't insist that it is normal. Okay, so let me now, before stating what we proved, let me recall one remarkable, I think, improvement of Margulis normal subgroup theorem is the Stuck-Zimmer theorem. So Stuck-Zimmer theorem says that if G is as above, so suppose G is higher rank and has T, like SL3R, but not SL2 times SL2. The theorem does not apply for SL2 times SL2. Then every, okay, let me, okay, let me be more precise. So let X M be a PMP action of G. So G acts on a probability space, preserving the probability measure. Then every stabilizer is either trivial or a lattice. So this is if you want a measure theoretic counterpart of the normal subgroup theorem that Stuck and Zimmer proved. It's not so hard to show that it implied the normal subgroup theorem of Margulis when G has property T, and it's much stronger. But I should say that if G is not simple, I didn't write it, then you require the action to be irreducible, that every factor acts ergodically. So this is Stuck-Zimmer theorem, and they conjecture that T is not needed, so higher rank is enough. So the Stuck-Zimmer conjecture so T is not required. So in particular, so for any higher rank group, it should be true. So for instance, for SL2R times SL2R, every PMP action, which is irreducible, that every factor acts ergodically, the stabilizer is almost surely either trivial or a lattice. Now, this is still open. I think what we did is getting close to prove that. So we proved, we didn't quite prove this, but we proved something similar. I'll come to that in a moment. Let me just say that one thing that Stuck and Zimmer proved also in the case where where G doesn't have T, they proved the following theorem. They proved that in higher rank, so all that stabilize a non-trivial stabilizer are co-amenable. And this they proved also without when you don't have T. So this holds also for SL2 times SL2. Also, when you don't have T, if SL2 times SL2 acts on a probability measure preserving space irreducibly, then stabilizer, non-trivial stabilizer are co-amenable. So this follow from what it did. It is emphasized in a later work by Hartmann and Tammuz, where they generalized it, but in the classical case, it's already in Stuck and Zimmer. And I may use it later. Okay, so now what we did. So let me now define the notion of confined subgroup. So this is a generalization, or it's something more general than the normal subgroup. So let's start with discrete group. So let gamma be a discrete group. Delta in gamma is called confined if there is a finite subset such that any conjugate of delta intersect F. Okay, let's say a finite subset, but not containing the identity. So any conjugate of delta intersect F non-trivially. So then delta is called confined, and the example is non-trivial normal subgroup. If you have a non-trivial normal subgroup, then of course it is confined. You can take F to be a singleton, which is any element in N, which is not the identity. So indeed, confined is stronger than is more general than normal. Now, in the non-discrete case, there is a debate how to. There are two ways to extend this definition. So, by the way, you can say that delta is not confined if you can conjugate it out of any finite set. So, if you want that the trivial group is a conjugate limit, is a limit of conjugates in the Chabuti topology, in the topology of subgroups. The trivial group is a limit of conjugates of delta if and only if delta is not confined. Now let me say that let G be a Lie group. Now, then the definition is the following: delta inside G is confined if there is C inside G compact such that G delta G inverse intersects C not in the identity element for any G. you can find a compact set that intersect non-trivially every conjugate of delta. So why I say that there is a two alternative extension for a non-discrete group. You can either require that C itself is compact and not contain the identity, and then you get one definition, or you can allow C to contain the identity, but you want the intersection to have something more than the identity. And for Lie groups, because you have no small subgroups, these two definitions coincide, but if you consider non-Archimedean, say, p-adic analytic group or more general, totally disconnected groups, then there are two ways to define. So here is a remark that delta is not confined. Delta in G is not confined if and only if you look at the conjugacy class of delta and you close it in the Chabuti topology, the topology of closed subgroup, you see the trivial group there. So what does it mean? It means that there is Gn in G such that Gn delta Gn inverse converge to the trivial group in the Chabuti topology. So the intersection with every arbitrarily large compact set will be only the trivial element if n is large. So then it's not confined. Or if you want another way to view it, so if G is semi-simple, and let's say X is the symmetric space, the Riemannian symmetric space, then delta is confined if and only if the manifold M, which is X mod gamma, X mod delta, the orbifold M has bounded injectivity radius. So you can imagine a manifold which is let's say it has it has bounded injectivity radius. So it's not necessarily compact. It not necessarily has finite volume, but the injectivity radius is bounded. You cannot find arbitrarily large balls inside the manifold. Then delta is confined. That's equivalent to say that delta is confined. And so in my work with Mikolaj Frakzyc, we called such a manifold uniformly slim. And by the way, so another example, if gamma inside G is a uniform lattice, and N inside gamma a non-trivial normal subgroup. So this is to emphasize the relation to the normal subgroup theorem. Then N is confined in G. So of course it's confined in gamma, but it's also confined in G. So so the theorem that a couple of years ago Mikolaj Frakzyc and I proved is that if G is SL3R, or if is higher rank, let's say if G is high rank, let's say simple. So we consider also semi-simple, but what's important that we had property T. So high rank simple as property T by Kazhdan theorem. Then confined subgroups are lattices. And this was the conjecture of Margulis. So it means that if you have a manifold, suppose the symmetric space of SL3R, you have a quotient of it which is a manifold of infinite volume, then the injectivity radius is unbounded. So you can find arbitrarily large ball. So if you can find large ball, it's equivalent to have infinite volume. So of course, if you have large volume, infinite volume, but also vice versa. And actually, we show that the random walk will spend most of the time in the very thick part. So that was the work with Mikolaj. But again, like all the other works that extends the Margulis normal subgroup theorem, we use a property T, and we used only so this work applied for that case. Now the new theorem that is the following. So I'll state first a version for lattices. So this is the new theorem with Uri Bader and Ariel Levitt and myself. So we show that this is also without property T. So if, in a sense, we extend the work with that I did with Mikolaj without property T. So let's let gamma be an irreducible lattice in a higher rank semi-simple Lie group, so like SL2 times SL2. Then if delta inside gamma is confined, then delta is finite index. So it's equivalent to be your finite index. So confined subgroup in high rank, like in SL2, z square root of 2, not just normal subgroup, but every confined subgroup as a finite index. So before telling you a few things about the proof, let me state a more general version, not just for lattices. So let me recall what is a URS. So recall a uniformly recurrent subgroup. URS is a minimal invariant system. So a minimal invariant set in a sub G. So sub G is the space of all closed subgroups of G. And G acts on sub G by conjugation. It's a conjugate acts, so that's a dynamical system. So sub G is compact, is with the Chabuti topology, the topology of closed subgroup. It's a measureable compact space, and G acts on it by conjugation. I like to consider measure on that set, like, and if so, I give some propaganda to my talk in the other conference that I'll do on Friday morning. Will be about the probabilistic methods to study discrete subgroup of G by studying invariant or stationary or more general measure on sub G. But URS is without measure. It just yeah. So that's a URS. So it's a minimal subset. Invariant under the conjugation. And now a definition. So a URS is reducible let's say G1 cross G2, but you can have more factors. And actually G2 can be trivial group. So then this could be a simple group if G2 is trivial. I say that a URS is reducible if it consists of subgroups of product group. Gamma 1 cross gamma 2. Sorry, so is that what I want to say? Yeah, okay. Okay, so let's suppose that G is not simple. So if G is a product of several factors, then I say that a URS is irreducible if it's not supported on such. Okay, let's say that if G is simple, then the only reducible URS is the trivial group. And now, so the theorem that we prove with Uri and Aryeh, in that case, so if rank of G is at least 2, then irreducible URS are supported on lattices, on irreducible lattices. Or if you want, we say that gamma in G is irreducibly confined if any URS which is contained in the conjugacy class, in the closure of the conjugacy class of gamma, is irreducible.
Are you writing something we are not seeing after that theorem?
Oh, I wrote, but I also don't see it on the screen. So what I wrote is that I said the theorem about URS, but then I said a definition of I said that a group is irreducibly confined if it doesn't have a conjugate limit, which is a product of subgroup of the factors, or is contained in one factor. So a subgroup is irreducibly confined if every URS inside a closed conjugacy class is irreducible, and the theorem that we prove is irreducibly confined is equivalent to irreducible lattice. So a subgroup that's what we prove. Okay, so let me now say something about the proof. So the proof is quite technical. So I told you that so in recent year I like to think about measures on sub G in many recent years about invariant random subgroups, and in more recent years about stationary random subgroups. But here in this work we had to consider even measures on sub G which are not stationary. So let me say a few words about the proof. So one remark is throughout most of the proof, so most of the proof we may assume we assume that delta is also coamenable. So in addition, so let delta inside G be irreducibly confined. It means that it's a subgroup that you cannot conjugate it. You cannot take a limit of conjugate of it, which is contained in one factor, and you cannot take a limit of conjugate, which is a product of two groups that contain in each factor. So if G is simple, then it just means it's confined, that you cannot take the trivial group as a conjugate limit. But if G is semi-simple, you don't want a conjugate limit that is contained in G1 or a conjugate limit that it's a product of gamma 1 times gamma 2. Then it's called irreducibly confined. And now, throughout most of the proof, we assume that gamma is coamenable. The proof relies on the fact that gamma is coamenable, which we don't assume. And at the end of the proof, we drop this assumption. So let me just say how we drop this assumption. So in general, so without this, so we how to drop this assumption. The coamenability assumption. So let's start with delta, which is some irreducibly confined group, and then consider the Dirac measure on delta. So that's the space that I'm looking at is the space of a closed subgroup or the space of discrete subgroup of G. And this is a measure there, a probability measure. And then I take some probability measure mu on G, some generating measure on G. And then I do this random walk. So I convolve with, and take Cesaro average. And I call this nu n. So nu n is a probability measure on the space of a closed subgroup of G. It's supported on conjugates of delta so far. But then I take some a limit of it, some weak star limit of this sequence. So it's not necessarily converged, but take any limit, then this will be stationary. It will be mu stationary. And then by results from my paper with Frakzyc, which basically, I mean, the main part there is a remarkable theorem of Neveu and Zimmer, but about general stationary action. But when we apply it for the action on discrete subgroup, then you get that stationary is invariant. So so stationary is invariant. That's by Neveu-Zimmer, and then what I did with Frakzyc, and then invariant by Stuck-Zimmer means that it's supported on coamenable subgroups. That's what I said that Stuck-Zimmer proved, and then you see that this implies so this measure nu infinity is a measure that's supported on the closed conjugacy class of delta. So you see that delta will have a conjugate limit which is coamenable. Now suppose we prove the theorem under the coamenability assumption, then this implies that the conjugate limit of delta will be a lattice, and then this plus local rigidity will imply the proof. So if delta, we'll see that delta will have a conjugate limit which is both irreducibly confined and coamenable, then it will be a lattice, and then it will be and then delta itself must be a lattice by local rigidity of the limit. So that's a trick. So we can assume that that delta is co-amenable. So now how does it help us? So it means that L2 of G mod delta has almost invariant vectors. So you have function Fn inside L2 of G mod delta, which are asymptotically invariant. So Fn has norm 1 and they're asymptotically invariant. And I suppose that G is, let's say, G1 cross G2. Now the trick of Margulis. So this is something that we borrowed from Margulis' proof of the normal subgroup theorem in the lack of property T. He has this he has this wonderful lemma that we reproved, because we proved a more general lemma, but he said what Margulis did, you can modify Fn. One can modify Fn to Hn. Let's call them Hn, also in L2 of G mod delta, such that Hn are asymptotically invariant vector, asymptotically invariant with respect to G1, but not with respect to G2. So there will be some uniformly non-invariant with respect to G2. There will be some single element in G2 that will move each of them by at least epsilon, for fixed epsilon. And Margulis in his paper do it under property that he called property Q, which is equivalent to say that GK is a Gelfand pair. But we did it much more generally for any locally. So our only assumption is that G is locally compact and has compactabilization, like that's the assumption in the Bader Shalom work, and in their extension of the normal subgroup theorem, and that's what we use here. So that's we get such a sequence which is asymptotically invariant with respect to G1, but not asymptotically invariant with respect to G2. Now consider Hn, let's say, square. So this is a unit vector in L1 of G mod delta. And I consider it as a distribution or a density of probability measure on G mod delta. Now there is a map from a G mod delta to sub G, the space of a closed subgroup, which sends the coset to the conjugate, and let nu n be the push forward of the probability measure that Hn square define. So nu n will be some probability measure on the space of discrete subgroup, and if you think of it, nu n will be asymptotically G1 invariant, but uniformly non-G2 invariant. Now you take a limit of that. So here I'm cheating. This is, I'm telling you a lie, but the lie somehow explained the idea behind our proof. So if I want to take a limit of this nu n, and in the limit I will get a measure which is G1 invariant, but not G2 invariant. And and this, so there is so here is a nice lemma. It's also from my paper with Frakzyc. So the lemma is the following. So let G be G1 cross G2, be any locally compact group which is a product, and acting on the XM. So that's a probability space, and suppose that almost surely the stabilizer are discrete and project densely to G2. So almost every stabilizer is discrete and project densely to G2. Then if M is G1 invariant, then it is also G2 invariant. So if it's G2, then it's G invariant. So that's a nice exercise, I think. So if you have a measure which is on, let's say, on discrete subgroup of G, which project densely to G2, if it's G1 invariant, then it must be also G2 invariant. And this somehow show you that there should be a contradiction, because now we have nu n which are asymptotically G1 invariant, but uniformly not G2 invariant. So if you take a limit of that, then you get something which is G1 invariant, but not G2 invariant, and it's supported on discrete subgroup that project densely to each factor. That's the irreducibly confined assumption implies. However, this is false because, of course, a limit of uniformly non-invariant measure may be invariant. So that's something you cannot take to the limit. So that was just an inspiration. You cannot get a contradiction for that. What we did, the proof is actually quantitative version of this idea. So instead of going to the limit, we prove a quantitative version that allow us to do all everything before the limit, and say that if you have such a measure, and if it's enough invariant under G1, it should also be almost invariant under G2. So and this is this is technically, it takes several pages. So that's to see that you have to look in the paper, or it doesn't. Okay, it's not. It's still preprint. We didn't publish anything. Okay, so it's the first time I speak about it. So so this is what I wanted. So let me just say, what did we prove about? What is the version of Stokes-Zimmer that we proved? So let me just recall. I already said, but delta inside G1 cross G2 is irreducibly confined if no conjugate limit is contained in one factor, and delta is not a product. It's not delta 1 cross delta 2. It's not a product of something in, or so if you want, so no conjugate limit no conjugate limit and delta is not a product, is that enough? Or delta that, so no conjugate limit is either contained in one factor or a product in one factor or a product. Delta 1 times delta 2. And so if you want, we prove that so Stokes-Zimmer conjecture was that if G1 times G2 acts irreducibly, which means that each stabilizer it's irreducible. No, it means that each factor acts ergodically. Then it's supported on lattices. What we prove that if you have so Stokes-Zimmer theorem in the language of IRS, it says that IRSs, irreducible IRSs, are supported on lattices, on irreducible lattices. What we proved is that if you want that irreducibly confined IRSs are supported on lattices, but we cannot do that without this assumption. So maybe let me just state another conjecture that it's imply or the Stokes-Zimmer conjecture if you can prove it. So it is conjecture that let's G be SL2 cross SL2R and gamma inside G coamenable, and let's say discrete, and project densely to each factor, then gamma is the lattice. So this is
we cannot see what you wrote for the conjecture after first line.
So I assume you will see it in a few seconds. So this, it's a conjecture that is equivalent to the Stokes-Zimmer conjecture, but it doesn't. It's about discrete group. It's not about PMP action, and it's not about. It's just a different statement that doesn't involve PMP action or IRSs. It just say a discrete group that project densely and is coamenable is a lattice. That's the conjecture, and this is still open. My feeling is that we are getting close to it, but I don't know. What we proved that if in addition you assume irreducibly confined, then we proved it. And which is good enough if you restrict to discrete subgroup of lattices, of irreducible lattices, but it's not good enough for discrete subgroup G. So yeah, okay. So now I think I need to finish because the time is yeah. So let me finish. Yeah. I don't see any of you, so I don't know.
Maybe it can change. Okay. Yeah. We also don't see you, but now maybe you can see me.
Yeah, I can see you. Yeah.
Not the audience, I think. Thank you for a very nice talk.
Yeah.